Patience, little technical difficulty. I want to remind people, right after this talk, I believe there's a photo session which is just outside, Jethro? Outside the door there? Okay, great. The next speaker is Leonardo Rastelli, who will tell us about 4D superconformal field theory and VOA correspondence.
Thank you very much. It's a pleasure. It's an honor to be here. I'm an outsider, as you know. I'm a physicist, so I have to make several disclaimers and apologies in advance. Clearly, my style will be somewhat different. I will use often sentences in the natural language, which is my English with Italian inflection rather than symbols. I hope I understood in recent months your language, but please correct me if I got it a bit wrong. The general statement I want to start with is that this subject, I didn't look for this subject. This subject found me. We were exploring the very rich physics of four-dimensional quantum field theories, and we stumbled into what looked like a piece of deep mathematics. And so we started to learn and then to work on it. And that is basically what I have to offer you today, a set of experimental findings that we just found in the wild. And they seem to be calling for some more serious mathematical work. The other thing I want to say, please interrupt me. Probably have more slides than I can go through, and I've noticed this week that you're an extremely polite and quiet audience, and I do not like that. I'd rather be heckled than ignored, and believe me, I can take it. So be as aggressive as you wish. So the starting point is in 4 dimensions. So we live in 4 dimensions. Not that that ever prevented theoretical physicists from pretending we live in a different number of dimensions. But 4-dimensional physics is extremely rich. And we're interested in a special class of 4-dimensional quantum field theories, which are both conformal and supersymmetric. And this is a very complicated structure, which, of course, to the satisfaction of mathematicians has not really been fully axiomatized, but nevertheless, we think we really know what we're doing. We think we really know that this series exists and they can be characterized from a variety of perspectives. And the first slide is about the algebraic characterization. So I'm writing here something that should be very familiar to all of you. This is an OP kind of structure, except that it's not in 2 dimensions. It's in 4 dimensions. There's no holomorphic requirement whatsoever. And moreover, these conformal dimensions are not required to be integer or half integer. Nevertheless, this expression makes perfect sense if you understand it properly. And the way to make sense of it is to not regard the OP as just encoding some formal powered series, as you are used to in your algebraic world. So we need to include an analytic definition about convergence of this series, etc., which is what makes the subject, of course, much harder than a purely algebraic characterization. Nevertheless, we really think we know how to do it. And in several concrete examples, we can compute these numbers, which sometimes take very interesting irrational values. And because we're dealing with 4-dimensional theories with n=2 supersymmetry, the relevant superalgebra is this one. So if you count the number of Cartans, so there's SU2, 2, which is just the conformal algebra in 4 dimensions, and then there's an SU2 and UR. This is the bosonic sum algebra. And so if you count the number of Cartans, there's 5 of them. And so a generic operator can be characterized by this list of quantum numbers, which I have conveniently color-coded for you. E would be the conformal dimension. Big R and little r are the Cartans of this global part, which physicists call the art symmetry, and big R will be green and little r will be red. And then there's Lorentz quantum number denoted by half-integer spins. So for generic choice of this quantum number, this is very complicated. And then the game we're going to play is to restrict this quantum number in such a way that we get the simplification. In fact, the simplification we will get will land us into the purely algebraic world of VOAs. But before I do that, I want to tell you another way to think about this class of theories, which is from the point of view of their geometry. And it's a very rich story. And simplifying somewhat, there are 2 very interesting geometries you can associate to 4-dimensional n=2 theories. One is called the Coulomb branch. And these are geometry in the sense of a variety of vacua that have zero energy. They preserve their vacua, so they have zero energy, and on this vacuum you preserve the maximum amount of supersymmetry. And again, these are interesting algebraic geometric objects about which I will have to say a little bit more later. And there is a basic dichotomy. You can either break the U1 and preserve the SU2 or vice versa. And it's one of the enduring mysteries of the subject that the description of the theory on these two different branches is extremely different. The mathematics that enter is very different. So many of you may be familiar with Cyber-Witten theory. Cyber-Witten theory is the realm of the Coulomb branch. But today I will have basically nothing to say about that, and the hero of this talk will be more the Higgs branch. So a little bit more about the Higgs branch. The Higgs branch in a conformal anechoic theory is a hyperkähler cone. So in vanilla cases, which by now are just a tiny minority of the whole landscape of theories, in cases where we know how to write down an explicit Lagrangian description in terms of some gauge group with some Miller content, etc., then you can describe very explicitly the Higgs branch as the hyperkähler quotient. You set to 0 some moment maps, and then quotient out by the complexified gauge group. But this is not something you always have, and so the more intrinsic characterization is something you will like, is a purely algebraic one. It's in terms of a ring, a commutative ring. The commutative ring is obtained because if I make this very special choice of quantum numbers, and it turns out that the OP I had earlier becomes regular, and so it defines a commutative ring structure. And what's more, it's actually a reduced C algebra in all examples. I don't know how to prove this in general, but we're confident that that's the case. And so the idea is to identify the Higgs branch, which is a variety, as, well, by the standard algebraic geometry dictionary, the Higgs chiral ring is the coordinate ring on the Higgs branch. And so we will forget about the metric, although I'm sure there are some interesting structure in the hyperkähler metric, and we'll think about this purely in algebraic geometric language as a holomorphic variety. And the fact that the Lydian hyperkähler structure means that actually there is a holomorphic symplectic form that you can use to define a bracket on the ring of functions. And moreover, the R grading, remember I started with operators have conformal dimension equal to 2R, so there's hidden there's an R quantum number, defines a cis direction, so this is a cone under that cis direction, and generators which have in our convention assigned R equal to 1 are special because they correspond to global symmetries of this variety. Those are usually called moment maps. So again, these are kindergarten examples. You take C2, that's RH, and it's just a polynomial ring in 2 variables, and the Poisson bracket is just the standard one. We can treat C2 mod Z2, and then of course we can describe this in terms of a quotient in 3 dimensions of, we have 3 variables subject to the condition that the sum of the squares is 0, and the bracket has a canonical SL2 type algebraic structure, because indeed all of this, because indeed the R assignment of the J's is 1, so all of them are moment maps, and this space has a SL2 symmetry. In a slightly more sophisticated example, of course, I could write all the climate singularities, but the next one is a quotient by Z3, where now we have still 3 generators, but one of them is special. It's the one that defines the U1 isometry of the thing, and the others have weight 3/2, and, well, that's the Poisson bracket, etc. So these are truly the baby example, the simplest examples you can have, and there is an extremely rich story. If you scan over the space of 4-dimensional T, you can find pretty much any symplectic cone has ever been dreamed of is there. So I seem to be, okay. So the idea is that we're not going to carve out of this complicated 4-dimensional story a much simpler algebraic structure, which is still, of course, extremely rich, turned out to be a VOA. And so the idea there's going to be a map from these somehow ill-defined categories of 4-dimensional into 2 superconformal field theory in the category of VOAs. I'm not going to go through the details of the construction, but the idea is that because the theory is supersymmetric, there's a certain natural nilpotent operator, which is schematically of this form, and if you restrict to the cohomology of that operator, that forces the local operator to lie on a plane. That's the first thing that you find. And what's more, in homology, the z-bar dependent drops out. So they define a purely meromorphic structure, which has the structure of a VOA. So let's first think of this space as a vector space. So as a vector space, this is a subset of the full set of operators of the four-dimensional theory, which actually, remember, we had 5 cartons, and there's going to be 2 conditions of them. So at the end of the day, this subspace, which we call the space of Schur operators for historical reasons, is going to be characterized by 3 cartons: big R, little r, those are the R-symmetric quantum numbers, and the spin L on the plane. And under this map, any such Schur operator gives rise to a holomorphic field in 2 dimensions, whose holomorphic dimension is this sum. So little l is always non-negative, and so you see there is an inequality between h and r. Big R goes from 0 to little h. And in principle, if you know the map, then you have a grading by the vector space by 3 quantum numbers, but you may not know the map. You may just know that the resulting VOA is given to you abstractly as a VOA, and as a VOA, the only quantum numbers you may only have access to is little h. So it turns out that this U1R is interesting, but for simple, I don't want to make the story, it's already complicated, so I will focus on operators where this R is exactly 0. Sorry, is there something? And the big R is more subtle because it's actually, in principle, it's a quantum number that you can put in your vector space, you can grade it by it. But at the level of the OP structure, it only defines a filtration because you can prove that as you take OP, R can at most decrease. And again, it's very important that there's this half filtration under the hood, but we will, in general, not know how to impose it if I give you the VOA abstractly. Okay, so let me now list a set of structural properties. Sorry? Okay, I may not. Well, the filtration is, okay, the product of 2 operators, in the product, if I take the product, such the normal order product, R can only decrease.
So it's an increasing filtration.
So from that viewpoint, it's an increasing filtration. Yeah. So it's opposite to a Lie filtration where the number of derivatives can at most increase. Okay, so I've now listed a bunch of structural properties that we know, that we can just prove very rigorously from this construction. So first of all, it's a super VOA, so we can have both Bose and Fermi statistics. The VOA inherits a non-degenerate inner product from dimension, so we know that we cannot have any null state, so it's always a simple quotient. Very surprising, and this is a hint that we are not doing some random thing, but there's some deep structure here. A priori, the theory only had global SL2 symmetry on the plane, because I restricted myself to a plane, but somehow miraculously, that gets enhanced to a full-fledged Virasoro algebra in a very non-trivial way, as it turns out. And so you always have this is always a conformal algebra where the central charge is always negative, because it's minus 12 times a 4-dimensional central charge. You don't need to know what this means, but the 4-dimensional central charge is always positive. We can have both integer or half-integer conformal dimensions, but there's no speed statistical relation. So it's not the case that the integer ones are always bosonic and the half-integer ones are fermionic. There's no such requirement. And then, more or less by definition, the whole story was designed to generate this VOA as a categorification of the Schur index of this, this character that counts Schur operator, and so the vacuum character is the Schur index. So we can proceed. This is a bit conjectural, but I mean, you can assume it. V is always finitely strongly generated. If tomorrow someone finds a very exotic 4D where this is not true, we'll reconsider, but I doubt it. And then a very important property is that we know something about the strong generators of V, but not everything. So the generators of the Higgs chiral ring get upgraded to strong generators of V. So this is the sense in which V is a generalization of the Higgs chiral ring. Okay, so knows about the Higgs-Chiral ring, but it knows also a lot more. In fact, in general, V has additional strong generator, notably the stress tensor T. The only cases where that's not true, where T is composite, is it arises by the Siegel-Sugawara construction if the algebra is just Kac-Moody. But I know that for you, Kac-Moody is perhaps 90% of the papers that get written in the subject, but for us, it's a complete infinitesimal part of this huge landscape of VOAs where Kac-Moody are just extremely special cases. There are things that I would love to explain in a little bit more detail, but I don't have the time. There's a certain functorial property. So if I perform certain operations, yes?
Yeah, so I'm very confused about that exception. So I would have expected that if you take Kac-Moody, then this Higgs ring would already have the currents, and therefore the stress energy generated.
So in 4 dimensions, okay, so I'm not sure I'm parsing your question correctly.
So the translation I'm making is that whatever this Higgs ring is, I take the spectrum, and it should be the C2 algebra of this Vertex algebra V.
No, it's more complicated.
Oh, the issue here is reduced versus not.
Yes, the issue is that I'm coming to that.
Okay, thanks.
These 2 properties, I'm going to mention this briefly. I think Tomoyuki Arakawa spent a lot of time last week, at least, giving a more mathematical version of what I'm saying here. These theories can be glued together by something called conformal gauging, and that corresponds downstairs to some chiral analog of the holomorphic symplectic quotient. And then if we move out on the Higgs branch in a certain direction, that corresponds to an nilpotent orbit of some subalgebra, that corresponds to the DS reduction of V. And these are the deepest properties, and I'm going to leave them for later. There's this hidden null filtration, and then there are constants that come from 4-dimensional unitarities. Okay, so let me continue with my little tail here. And so conceptually, a very nice surprise that, again, it's experimental physics to some extent. There are no 2 known 4-dimensional theories that have different VOAs. So it appears in that sense that this VOA is a perfect invariant of the 4D theory, which is, of course, huge welcome news, because who knows how to classify 4D theories, but if this is really true, you could hope to classify the special kind of VOA that arise from 4D. It's also clear that the kind of VOAs that arise from 4D are very special. So the map is injective, but certainly not surjective. One property I already mentioned is that the central charge is always negative. So for sure, these theories are non-unitaries. But as we're going to see, there's going to be a lot more weirdness coming in a minute. And so a first obvious question, can one fully axiomatize this subcategory of the space of VA that arises from 4D? It's going to be very special and perhaps amenable to a classification. And then a question which curiously turns out to be intertwined with it, could we dream of finding an even simpler algebraic structure, something we can distill from the VOA that still is a perfect invariant? And to this audience, actually, I can now go very quickly to the next few slides, because otherwise I will have to explain this whole language of C2 and Higgs scheme and Higgs variety, and associative variety and associative scheme. But that's the obvious question. Is the associative variety a perfect invariant, yes or no? If that fails, is the associated scheme a perfect invariant, yes or no? So these are very obvious questions that to this audience should make sense.
Sorry for a question that is tangential, but is there any way of enhancing your Higgs branch in such a way that it becomes a scheme?
Well, you're too smart. You're anticipating our whole research program. So that's what's coming. So, why can't I do this? Okay. So I can go very quickly here. This is just the basic definition that have been actually made many times this week and the past week. We can define the standard RV space by quotienting out by operators that contain derivatives. And so if the original V is strongly finitely generated, then this is just a polynomial ring in the formal value associated with each of the strong generator quotiented out by the nulls. And as you are aware, we can define a normal ordering. So obviously there's a commutative algebra, but also there's a Poisson structure which is induced by the bracket in the VOA. And in general, RV is not reduced. So these are canonical definitions to this audience. The reduced version of RV is what's called the associative variety, XV. And then if I put a tilde, following Arakawa's convention, that is when I'm not reducing it, and that's the associated scheme. And so what is the relation of these objects to four-dimensional physics? And so you will forgive me if I'm going to change the name now. It's not associated scheme. If I tell my physics colleague associated scheme, the first thing I'm going to ask is associated to what? So I'm going to call it the Higgs scheme. And so the procedure is this. We have the 4D theory. There is this canonical way to construct the VOA, and then from it we can construct the associated scheme. And the beautiful result, which is conjectural, so now I'm entering this more dangerous conjectural territory, which is purely experimental. But this is something we really have checked in many, many, many examples. We are confident of it. Is that very beautifully, the associative variety is the Higgs branch. Or equivalently, the reduced part of RV is the ring of functions on the Higgs branch, which is this Higgs chiral ring. And what follows from this in the terminology of Arakawa Kawasetsu, because the Higgs branch is a symplectic thing, in fact, in your languages, it has finitely many symplectic variety, it follows that if our conjecture is correct, that all these VOAs are quasi-Lis. However, the conformal vector is not an element of the Higgs chiral ring. It is not at all. And so it follows that the conformal vector must be nilpotent in RV. And nilpotency of the conformal vector in RV by one of these recursion relations that you can use to derive differential equation for the one-point function of the torus gives a modular differential equation. So this has the extremely striking consequence. The Schur index, which was originally defined as a purely formal way to count Schur operator, is actually a modular object. And that's what we have really checked. We have computed Schur indices in hundreds of cases, and we have checked that obey modular differential equations, which is strong evidence for this conjecture. And so, to summarize, most of our theories have a Higgs branch or have a non-trivial associative variety, so they cannot be Lis. But conjecturally, if this conjecture is true, they are quasi-Lis. And so this actually now gives us, from a physicist's perspective, a very beautiful and very natural extension of the standard Higgs variety by nilpotence. And now the question is this a perfect invariant? Sorry, I should first tell you, the Higgs branch is clearly known to be not a perfect invariant. In fact, there are infinitely many superconformal field theories where the Higgs branch is just a point. So very clearly, if the Higgs branch is a point, then the associated VOA is Lis, but obviously that doesn't characterize the 4D theory, because you can have many Lis theories that all have trivial Higgs branch. But very remarkably, again, this is a bit more tentative, but we are checking this in more and more cases. It turns out that this much simpler object, this associated scheme of the VOA, is a perfect invariant. And so if true, this is very remarkable, because we distill this extraordinarily complex four-dimensional gadget to a finite dimensional algebra. Correct. Correct. So that, in that sense, it's non-natural. At the end, I will have some comments about that. Nevertheless, it's something you can do, right? So this is a well-defined map. If I hand you the 4D theory, there's a perfectly well-defined map that defines a VOA, and then I come to you, and I ask you to compute the associated scheme. Okay, so so far, lots of words. Let's do a few examples. So there's an infinite sequence of theories. You don't know anything about it other than they're labeled by an integer n. They're called Algebraic theories, labeled by these two A's. And they're known to have trivial Higgs branch. And rather remarkably, the map to VOAs is that they correspond to the Virasoro, to the simple quotient of Virasoro at central charge of the minimal models 2, 2n plus 1. And famously, the RV is just the ring in a single variable modded out by t to the n. And so clearly the reduced variety is trivial, but the scheme is not. And well, that's what allows us to distinguish these theories. In fact, you could say, what about if you find another minimal model that has the same X scheme? Well, it turns out we couldn't. So you search through the whole landscape of theories, and it turns out that theories have this particular scheme. It's only this one. So in this context, this is a perfect invariant. More non-trivial example. Still trivial Higgs branch, but there's a very nice sequence of theories that are now labeled by 2 integers that are WP minimal models. The way to characterize them for this audience is that the one that arise from the S reduction by the principal embedding of SLP at the boundary admissible levels. And again, we check this experimentally by brute force in Mathematica. We construct, never mind. We construct the nulls, and then we construct the varieties, we construct the schemes, and again, at the level, if I look at the W3 examples, for example, the level of the variety, it's trivial, but the scheme is non-trivial, and that's what distinguishes these different theories. Non-trivial Higgs branch, for example, C2 mod Z2 is sort of the next simplest thing you can think of. Again, it's an infinite sequence of theories whose VOA is actually rather beautifully associated to SL2 at the boundary admissible level. And again, for this audience, I can go very quickly. As a variety, this is just the same. C2 mod Z2 is just this 3 variable modded out by this Casimir. But at the level of the scheme, that's not the case, and the scheme distinguishes this infinite sequence of theories. Okay, so, and now, of course, the obvious question that comes to physicists, and we were very happy to see that the same question had been asked in mathematics, more or less contemporaneously, but of course, we didn't know how to do it, and you did. So given that it seems that RV is a perfect invariant, can you actually go back? If I just hand you RV, can you reconstruct the full VOA? And the answer is in general no, because, for example, if I take 2,7 Virasoro and 3,4, they have the same RV. And so clearly the map is many to 1. But however, in some cases, as we have heard, RV suffices to reconstruct not quite the full VOA, but its commutative limit. And so this is a story I can go through quickly. So there's a canonical filtration, which is by the number of holomorphic derivatives. And the associated graded defines a commutative algebra, which is, in fact, the Vertex-Poisson algebra. And the simplest way you can construct the Vertex-Poisson algebra is start with a finite dimensional Poisson algebra and add generators corresponding to formal derivatives subject to the original relation of their derivatives. For example, if I start from this variety and from this scheme, from this fat point with t to the n is 0, I can construct this infinite jet scheme by adding formal derivatives and modding out by all the derivatives of the original relation. And it's a rather simple theorem in this business that there is a surjective morphism of differential algebra with this infinite jet scheme and the associated graded. And then you guys, Ekeren and Heluani, then defined the, sorry? Oh, I'm really sorry. That's terrible. My deep apologies. So this notion of classically free VOAs if this kernel is actually 0. And so if the kernel is 0, you can, I'm really sorry, of course it's going to be a cut and paste, so it's going to be misspelled everywhere. And so if the VOA is classically free, then you can go back at least to this Vertex-Poisson algebra with its commutative limit. And, well, okay, this is an experimental science. In all the examples we have checked so far, the VOAs that come from 4 dimensions are classically free. We haven't checked, I mean, I cannot claim we have checked enough. So this conjecture is on a somewhat shakier footing than the one that said that all these VOAs are quasi-Lis. But the evidence is still rather non-trivial. So we find precisely the Virasoro 2,2n plus 1. We find SL2 at boundary admissible. We find these W3 examples that come from SL3 at boundary admissible, and I don't know. I try to get some sharp statement from you guys the last 2 days, but you guys are extremely cautious. But anyway, it seems plausible that this would be bound, that this would also be here.
When you say that you're checking this, is the check a physical check or is it a numerical check?
It's a numerical check. It's an entirely numerical.
Drummer base or whatever keyframes
Correct.
the computer guy and you get it into the same.
Yes. But these checks are very hard. We could at least, either we're bad with computers, which we might be, but it's not so easy to do this calculation.
I have a safe package that does this for any vertex.
We will be we're very happy to use it. We do this in Mathematica and it's very slow. What's more interesting actually, you could say, okay, well, these are very simple examples, but this subject is trying to tell us something, because there are cases where this conjecture could have been falsified, went very, very close to being falsified, but in fact it was not. And so for that I need to tell you a little bit of this story about nilpotent Higgsing. Assuming that the original theory has some global symmetry, it turns out that this symmetry actually acts on the Higgs branch. This is what I was telling you earlier. These are degenerate of the Higgs branch which have R equal to 1. They correspond to moment maps. And so a procedure that should be familiar to you from this work of many people in the field in terms of associative varieties and symplectic and whatever, nilpotent orbits, is the story of nilpotent Higgsing. So you can consider an embedding from SL2 to G star, and you pick a negative root, and so you have an element, a nilpotent element, and then in the inverse image of the nilpotent element, you fix a point of your symplectic cone. And physically, if you put yourself at that point in the moduli space and then flow to low energies and remove some free stuff, that's the idea of the normalization group flow, you will find a new theory. So that's what happens upstairs. What happens downstairs is just linking software reduction by this nilpotent element. And so, for example, the Higgsing of this particular theory gives this particular theory, which in your language means that the DS reduction of SL2, a boundary admissible, gives you Virasoro at 2,2 n plus 1. Now, we can use this to find a cute example of a near failure, because we happen to know there's a theory. It doesn't matter what it is, but for us, physics corresponds. We take 2D3 branes and put them at a certain singularity. And we know the central charges and we know the level. So the simplest guess is that this theory is SL2 at minus 17 over 10. And then you get very nervous because this is not boundary admissible. But then we know, well, is this compatible with the idea if I separate the 2D3 branes, I must get 2 copies of the theory with a single D3 brane? Well, what that amounts to is Higgsing. And so 2 copies are just 2 copies of our old friend, which is Virasoro at 2,5. And if you do the DS reduction of this guy, you don't find that. You find Virasoro at 3. And so actually you should really consider, take serious the possibility of extending the original gadget. And it turns out that Katz and Makimoto told you what are the possible extensions. And there's only one that is compatible with 4-dimensional requirements. It's by this gadget. And if you do that, that works beautifully. Then you find precise 2 copies of the single D3 brane theory. And so I would be willing to bet a dinner at, I don't know where, at the Churrascaria in Rio, that this particular extension of SL2 at level minus 1710 is actually classically free. Okay, so that leads us to speculate that classical freeness is a general property, and if that's the case, we will predict a huge class of extremely non-trivial examples of classically free VOAs. For example, these, the Lin series, some of them, for example, D4 at level -2 or whatnot, it's not even admissible. A plethora of Argyles-Douglas series, class S, etc. This is a question I would perhaps, after my talk or some other time, I'd love to chat with you about. What about higher chiral homology of these VOAs? Are, in the example that I gave, are all of them trivial or not? Is it an interesting thing we could look at? And so the summary so far is that the image of chi obeys some structural rigorous axioms and some more conjectural properties, which are experimental. And the 2 ones that I've emphasized today, the 2 properties I've emphasized today is the quasi-List property that I'm quite confident with, and much more tentative is this classical freeness. And of course, the open problem is to prove, for example, classical freeness, or more, perhaps less ambitious is quasi-List property, from the structural property that I listed earlier, except that I did not quite fully list them, and that's what I'm going to do next. And so the property that I skipped a bit on is this R filtration. So the idea is that secretly, for even the Virasoro algebra or any of the Kac-Moody algebra that appear in our context, they are not just graded by H. They have a secret additional grading, which is not obvious, and you have to carefully define. And again, this corresponds to the fact that in 4 dimensions, for each value of the downstairs conformal dimension, there's a finite number of sure multiplets that all map to the same thing. So in 4 dimensions, these are different objects, and they are distinguished by the value of big R, but in 2 dimensions, they all look the same. And so you have to disentangle this additional quantum number. And the additional quantum number, for example, is what characterizes the Higgs branch. So here is some quick story. So obviously 0, 0 is the vacuum, 1, 1 are the affine currents, 2, 1 is the stress tensor. We know certain interesting facts about 4-dimensional physics that tell us, for example, that this space is allowed. If H is equal to R, this is the Higgs chiral ring. And so the idea is to endow the VOA with this additional structure and then presumably additional condition that would tell us that the associative variety is necessarily this particularly graded component of the VOA, for example. And a very interesting problem with this R filtration is that the OP is short. Given that this R arises as the Cartan of a non-abelian group, there's a triangular inequality that is implicit in the story. And so you can only get a finite amount of terms of this kind on the right-hand side because there is a triangular inequality needs to be big. A very similar idea was used in my work with a similar set of collaborators in 3 dimensions. In 3 dimensions, rather than restrict to a plane, we restrict to a line. And then we find a topological one-dimensional theory, which happens to be a quantization, in the sense of Konciewicz et al., of the Higgs branch. And so we have a similar short start product in that context, which was used by Ettinghoff and Raines to great effect in a paper a few years ago. Okay, so, and finally, the 4-dimensional unitarity. So we also, this is the 4D theory has lots of properties which are a little bit hidden. One thing we know about 4 dimensions is the Cpt theorem. And what the Cpt involution tells us that there actually needs to exist an antilinear automorphism sigma of V, which preserve this grading and squares to -1 to the 2R. And this is the, if you're able to endow your VOA by this R filtration and you know this automorphism, both of which you in principle know if you know the full map from 4 dimensions, then although the 2D theory is not unitary, this particular combination is positive. So there's an additional minus sign that comes from knowledge of R, essentially. And so you get alternating signs, but in a predictable way. That defines a positive definite inner product on the 2D theory. And, okay, so, sorry. And so I'm nearing the end of my talk. So this is something we're extremely optimistic about with Chris Beam a few years ago, that using this additional structure, we could prove all sorts of beautiful things. We are still optimistic about it, but we haven't been able quite to do it. But that's our hunch, that this additional structure would actually be able to, for example, we will be able to prove, for example, that only this particular discrete set of central charges are allowed. And so both the quasi-Lie property and, if true, the freeness, classical freeness, should somehow be encoded in this kind of additional structure. Okay, so so I'm now addressing one of your objections earlier. It's true. The way I phrase the story, you construct the VOA, that's very natural because it comes from an intrinsic homological construction in 4 dimensions. Then from it, you define this associative scheme. That's a little less natural. And the reason is less natural is that story is based on the Lie filtration. And the Lie filtration is not something which is natural in 4-dimensional physics. What's natural in 4-dimensional physics is the R filtration, because that's the actual quantum number that we have in 4 dimensions. And so what we really should be considering is not so much this infinite dimensional vertex Poisson algebra obtained by the Lie filtration, the associative way with the Lie filtration, but rather the associative way with respect to the R filtration. And so that's different. There's a different vertex Poisson algebra structure that gets associated with the four-dimensional theory, and that's perfectly intrinsic. In fact, I don't have to go through the VOA to define it. It's intrinsically defined as a different cohomological construction directly in 4 dimensions. In fact, it was studied by Capuzzi many years ago, although very, very few people have worked on this. And the original VOA can actually be understood as a quantization of this vertex Poisson algebra in terms of some omega background. Never mind that if you don't know that story. And so what we would really like to do is to reconstruct this vertex Poisson algebra obtained from the R grading from a finite dimensional algebra, an analogy for how this gadget was constructed from RB. But it seems awkward. We don't know quite how to do it. We have a proposal, but Tomoyuki doesn't like it. Sorry?
In your examples, are you claiming that you get 2 different Poisson
Yes.
vertex?
Yes.
So if you forget the gradings, are they still different Poisson vertex?
They have different generators, for example. For example, let's look at a simple example. SL2 level minus 4/3. Then in the standard Lie filtration, you get the 3 currents and their derivatives. But in our story, because T is treated differently, T comes back to you as a new generator if I do the associated with respect to R. So,
It is true also for the standard increasing Lie filtration.
no, that would not be the case.
The T goes out.
No, it does not go out. T is just J squared. T is not a generator.
Yes, it is. So in the standard increasing Lie filtration, T preserves the degree.
Yes, so that's why it's not a new generator, it's a composite. So for us, precisely because in the standard story T has the same has the same grading as J squared, it's a composite. But for us, J is associated R equal to 1 and T is associated R equal to 1, which means that J squared is 0. So in your filtration, J squared is not 0, but for us J squared is 0. And then what used to be J squared comes back to you as a new generator we call T. And then the products are also different. So it's generally we can talk about it, but it's generally different vertex Poisson algebra. Okay, so, and then let me, a final slide before I conclude. So I focused on the richest story, which is this VOA story, where it's necessary to start from a conformal theory. But actually, it's clear that we didn't really use very much about the VOA. Most of what I told you today really is more intrinsic to the vertex Poisson algebra story. And so that actually, naturally, you want to ask the question, could I generalize the story in 4 dimensions to cases where the original theory is not conformal? And the answer is yes. This holomorphic topological twist makes perfect sense for any n equal to 4-dimensional theory, even if the theory is non-conformal. You don't get to define a VOA. You only get to define a vertex Poisson algebra that presumably you cannot quantize back to a VOA. But nevertheless, I would be tempted to make very similar conjectures in this story. And actually, this is the setting of another very completely mind-boggling, mysterious story. So I told you at the beginning there's the Higgs branch and there's a Coulomb branch. Everything I told you today is about the Higgs branch and some augmentation thereof. I could have given you a completely different talk, talking about Seiberg-Witten theory of these theories. And then on the Coulomb branch, you get to define completely different structure. Special Kähler geometry, Seiberg-Witten curves. It's a characterization of the same theory. And again, in that context, again, no 2 different 4D theories have the same special Kähler structure in Seiberg-Witten theory. And so, naturally, I start from my Higgs branch story augmented by nilpotence. I go back up, and then I go back down again, and I have a relation between wildly different pieces of mathematics. And the question is, can they be connected more directly? And there is a hint of that. So it turns out that the Schur index, which for us today is just the vacuum character of the VOA, can also be computed, at least in certain examples, by computing by a certain sophisticated trace on the Coulomb branch. On the Coulomb branch, you have a spectrum of infinite, we have an infinite spectrum of massive BPS states, monopoles, and those of you who are familiar with Seiberg-Witten theory, you have this intricate spectrum of massive states. And there are walls of marginal stability. So as you cross these walls on the Coulomb branch, the spectrum jumps. Nevertheless, Kontsevich and Sobian define certain wall crossing invariants. And this gentleman conjectured that a very specific wall crossing invariant you can define the Coulomb branch is equal to the Schur index, and it is in many examples. So this gives you a completely crazy connection between two completely different areas of mathematics that you can connect by going back up to 4 dimensions. Of course, the idea is that there should be an ultimate structure that encompasses them both. Okay, so remarkably, I am on time, and so I can conclude. So as I don't have to, sorry, I wanted to say this. Maybe given that this is a VOA workshop, you people despise vertex-Poisson algebras that don't come from VOAs. Maybe it's something that you really dislike, but if you don't, I think there are some interesting mathematics here. Okay, so, okay, I don't have to tell you that a generic VOA is a complicated gadget. Even rational VOAs are too complicated to be classified, but it turns out that the VOAs that we stumbled upon in our work seem to be very special. They are quasi-Lis and more tentatively, much more tentatively, to be honest, classically free. And so we will eventually like to axiomatize all their special properties, notably these positivity conditions that come from 4-dimensional unitarities. And perhaps this is a much more manageable subcategory that could be classified. And of course, if you classify them, very likely you have classified the space of 4-dimensional equal to the superconformal field theory, which would be amazing. And so, well, may the rich physics of 4-dimension inspire some deep mathematics. Thank you.
So are there some questions for Leonardo? Tomoyuki also is.
You don't. It's just that the Higgs, that the Schur index, so the Schur index is something that can be defined also in the non-conformal case, and it's just counting the operator, it's counting the states of the vertex-Poisson algebra. So the vertex-Poisson, in the same sense that in our story, the VOA is a categorification of the Schur index, in the generic case, the vertex-Poisson algebra is a categorization of the Schur index. So it feels, and this story of Cordova-Shaw doesn't care whether the theory is conformal or not. So in that sense, it seems that the vertex-Poisson story is the more natural setting. You don't have to use the conformality.
Anton had a question?
Yeah, Anton, you want to ask your question?
Yeah, I have a question. So you mentioned that you can get a super algebra for 4D. So what would be an example? All examples that I've seen are actually purely
bosonic? Anytime the 4-dimensional theory has fermionic Schur operator. So the simplest case, which is a bit of a cheat, is when the 4-dimensional theory has additional supersymmetry on top of n equal to 2. So the 4-dimensional theory has n equal to 3 or n equal to 4 supersymmetry. Then you get super algebra extensions. But there are more natural examples. For example, in class S, the moment you have higher genus, theory of class S associated to higher genus, you typically encounter fermionic operators.
Okay, so those are really fermionic. They're not Z-half bosonic.
No, they're fermionic. Well, I'm using the word fermionic in the sense they obey Fermi statistics.
Yeah.
That
Okay,
it doesn't mean that they have half odd dimension.
Okay. All right.
Yeah.
It's a comment and a question. So you said that in all the examples that you gave, or at least in the affine boundary admissible, and in the Virasoro case, you can distinguish the theory by RV, but not by the reduced part. But actually, something simpler also distinguishes them, which is the Poisson homology of RV. So I wonder if you can say something about the Poisson homology. You haven't used the Poisson structure.
I cannot say anything because I haven't thought about it, but we should discuss.
I think it doesn't seem that you're using actually the Poisson structure of
We are not
Fardy
using
itself.
that very much. That's true. So, but the Poisson structure is trivial in these list examples, right?
So for Virasoro it is, but not for the affine cases.
So the affine case is non-trivial. That's
Yeah.
right. But yeah.
And the Poisson homology of this distinguishes them, and it's just an easier vector space to deal with than the scheme itself.
That would be great.
Are there any other questions?
So you want to say there's an even simpler object? Well, that may be getting a little bit too crazy.
That at least connects directly
Yes.
with chiral homology. This is my hope.
Okay. I mean, again, this is if tomorrow we find a counterexample, it's experimental science.
So when you were
I
saying,
didn't prove anything. That's a great.
So when you were saying experimental, did you mean proof, or did you mean that you made?
Sorry, you mean?
You several times you referred to that you had experimental this or
But
experimental that. You mean that you had proof, or
okay,
you
so
did-
of course I'm partly joking. Some parts of my set are completely solid. They may not have been axiomatized in a way the computer recognizes them as a formal proof, but we are saying correct, rigorous statements.
So you did not.
Some
just
other
calculate
parts are
examples.
conjectural. The parts that are conjecture, for example, it's a conjecture that has passed many tests. It's this quasi-Lie property that any VOA that comes with 4 dimension is quasi-Lie. We believe it, but we haven't proved it. It's experimental in the sense that we have this world of theories that we did not define. It knows more than us, and we're just wandering in this beautiful space and observing. That is the very strong feeling that perhaps also mathematicians get, but certainly it's not up to us. There is a predefined space of consistent 4-dimensional quantum field theory, and we're just exploring it.
Okay.
That's the sense in which it's experimental.
Okay. Any other questions? And on Zoom, any other questions?
I don't think so.
Okay. So we can thank Leonardo one more time.
Thank you.